So let's take a look then. It's the first class I think that I need the visualizer on. You guys ever seen the movie Captain Fantastic? No?
I want to see that. I'm gonna watch it.
I watched that last night and it's amazing. And I thought, yeah, like your movie would be perfect.
Isn't it the one where the mom like, and then they like have to go back?
Yeah.
Yeah.
The
no,
dad
I-
actually, it's like self-home teaches them every
Yeah.
life skill. It is, it's really good. All right, so if we take a look here, this is the packet. The answers are up to here. Now this was a little bit weird because certain questions I took off the review. So if you take a look, I'm gonna put this in there. This is 1, 2, and then 3, 4, 5, 6, 7, 8. You may have been able to figure that out as you were working through it. But those are the actual review problems. So let's take a look. Any questions 1 through 5?
Yeah, for 5.
5.
Is it just my favorite reaction?
Yeah. So the magnitude of K, if K is greater than 1, what are favored equilibrium, products or reactants?
Wait, I'm at 5.
Yep. The magnitude of K. If magnitude means like the number, right? I'm sorry. Do I have a different packet?
This is like
Let me grab the other packet. Make it all difficult. Must be from a different view. Where is my packet of that? Unit is equilibrium, right? Is this the one you're talking about? Yeah, I must have had all of them on. Check one thing real quick. Yeah. Let's do it on. All right, number 5 here. For the system 2H2 plus O2 yields 2H2O, a reaction is started only with O2 and H2O in the container. If we only have this and this, what don't we have? H2. So what must happen? Yeah. The reverse reaction must be favored. Yeah. Like I've answered those already. Huh. Next.
What page was that?
That's page 19.
Okay, thank you.
Welcome. Oh, I did. Here we go. I'm a dummy.
Like, when it's
So if it's endothermic, heat is being brought in. So we add heat onto the reactant side. And delta H is positive because it's being brought into the system. If it's exothermic, we put heat on the product side, and if it's delta H, it's negative. Forward would be favored, and it would produce more product. Exactly. You got it. Heat is on the product side, so we increase temperature. That's like adding more product. Reverse reaction is favored to get rid of the product. Exactly correct. Any other questions? 5 through 10. I will put these answers on there. And then what I had was this, and I will recorrect the what do you call it? The answer sheet that's on there. Question? Any questions on the page 21, 1 through 5? Yep. What condition must be met in order for a system to be at equilibrium? So if we're looking at a system at equilibrium, basically you have to have a closed system. So a beaker with a reaction going on in there, that would be a closed system. Volumetric flask, yeah, like an open system would have both the system and the surroundings into it. A closed system, we would be looking at just the system. We would not be concerned with the surroundings. Closed system, no observable changes is another way you could say that. And you must have some amount of each product and reactant. Let's just call it each component. Okay. This is a list. Yep. The question. Yeah. So what must be met? These are the conditions. So we have 1, 2. Other than that, if it is truly at equilibrium, then what does that mean about the rate of the forward and the reverse reaction? Yeah, right. They're the same. Does that mean that the amounts of each product and reactant are equal? No, and that's what K determines. That's the ratio between products to reactants, right? Who's on top? Products. So that means if K is greater than 1, then the numerator is greater than the denominator. We have a more amount of products or a higher concentration of products versus reactants, and K is less than 1, then we have a fraction there. And that means that the reactants are favored at equilibrium. Can K be less than 1, Hudson? Hudson, can K be less than 1? How about one of the Gavins?
Yeah, it can be.
Yeah? Give me an example. I'm sorry. Let's try again. Maybe that's why Hudson didn't answer. Can K be less than 0? Can K be negative? No.
Wait, sorry, were you saying something? I could not, it like cut out again, sorry.
What are you trying to say, Hudson? Your internet connection is poor?
Yeah, it was. I could not hear anything, and then I heard my name, and like later, and couldn't tell.
This lecture?
Sorry, what was that?
Because you're playing Call of Duty while on PS5 while you're listening to this lecture?
No, I'm not.
That's slowing down your internet. You must be trash on there, man. If your internet's always messing up.
I'm like on like some pretty good internet, and it's only the Chromebook that messes up. Like my phone and everything else is fine, but it's only the Chromebook.
Here right now, maybe you can talk to him about that MSDWT property. No. All right, closed system, some amount of each. Does everybody understand that one? That one's important. When we're doing those ICE tables, that means that if anything is zero, products or reactants, that determines whether or not we're going forward or reverse. And then the rate of the forward, that is Q at equilibrium. Instead of solving for K, if we're not at equilibrium, what do we call it? Q. Is Q any mathematically different than K other than not being at equilibrium? No, it's the exact same, product over reactant. Let's go ahead and do one of those since we have number 4 right here. 3, I guess. Well, no worries. Why are solids and liquids not included in the equilibrium expression? So those are concentrations. And if you have a solid or liquid, it's considered to be one, right? Because concentrations are usually moles per liter. Yes. And if we take a look, it's solid, so it basically just becomes 1. We don't worry about the concentration for it because it has its own volume. If it's present, it's 1. Same with liquid, because they're the same throughout. They're not like a concentration, so they just become 1. That's the thing, right? In our heads, we have to get over the fact that aqueous, even though we know it's in like a liquid state, it's not a liquid, right? A liquid is different than something that's dissolved in water. I know that's hard in our mind, but that's why we made this thing called aqueous. So if we take a look into, we're going to square that because of the 2 here. H2O. And at the bottom, NH3, O2, 2. Products over reactants. All of these are gases, so all of them have a participant, they're placed in that equation. Out of all those equations, which one has something that would not be placed in it, would be replaced by 1? C actually has 2 objects that won't be placed in it, right? How about D? He has 1. Yep. So then we know that the reactants are the new favorite for that, right? If K is less than 1, or I'm sorry, if K is greater than 1, products are favored at equilibrium. If K is less than 1, reactants are favored. I never had him do that. That was weird. Yeah, right? I guess it. Yeah. No. Yeah, he's kind of just standing there. I actually said, do you need anything? And he just looked at me closely and went, kind of, yeah. Yeah. I can't wait. Maybe it's going to call Hudson. Hudson gets a call from the principal. All right, 7 or 8. Any questions there? They have a lot of parts. And again, this is the 7 and this is the 8 on the answer guide. I will put this into I will scan this in and put this I'll change that as the answer to the review. And then I will also add, was this not on there? Okay, so I will also add this review. Number what? 5. All right. That's what this is. The magnitude of K, if K is greater than 1, products are favored. If K is less than 1, reactions. Q is at any time. At any time. How do you do any? Oh, any time other than equilibrium. Actually, it can be at equilibrium. The actual value of Q tells you whether or not you're at equilibrium. If Q equals K, that's at equilibrium. If Q is greater than K, then it has to favor the reverse reaction. If Q is less than K, favors the forward reaction. Pressure works by the number of moles. So let's take a look, see if we get one on the back. Here we go. What would the effect of a pressure increase have on the following equilibrium? So this has 6 moles on this side and 2 moles on this side. So which is bigger? I'm sorry, which is less because we're increasing pressure? 22. That's way on the back. So out of 6 and 2, which is smaller? 2, right? Hardest question of the day. So we're going to favor the side with the 2 moles. When you talk about an increase in pressure, that puts the squeeze on it, right? That's like a bunch of people piling into the elevator. It's going to take up the least amount of space that it can. We know that 1 mole of any gas at STP takes up 22.4 liters of space. It's going to put the squeeze on it, and it's going to go down. It's not going to pick up as much. Yeah, you got it. Since all of these are the increased pressure, each time you look at the smallest number of moles that it make, it's going to do that. Any other? Do I not have this just printed differently than this? So it must it's just printed differently. Yeah. So 8C is right here. I assume this is the same 8C. For the reaction 2HF yielding H and F, the K sub BQ is 1 times 10 to the, what is that, negative 95th. So as products or reactants favored at equilibrium. Yeah, right. This is very, very, very small K. If at equilibrium, a 1 liter container contains 2 moles of HF and how many moles of H2 and F2 are formed. So if we take a look, K equals H2 and F2. And at the bottom, we have the HF, which is 2 moles per liter squared. Well, for every 1 H that forms, 1 F forms. That means that the concentration of H and F are going to be what? X and equal, right? So we get K equals X squared over 2 squared, which is 4. So then K is we can take the square root of this whole thing, right? K is 1 times 10 to the negative 95th. We multiply that by 4, we get 4 times 10 to the negative 95th. We square root that. Tell you the truth, I don't know how to do square root of the exponent in my head. Does it change? Did I multiply the 4 wrong then? Okay. So we take the square root of 4 times 10 to the negative 95th. And we get 6.32 times 10 to the negative 48. I guess that's something that you can't do in your head then. Is that the deal? Like in my mind, I was like, maybe I can take the square root of 4, which is 2, and then yeah, I was sitting there trying to think, but the 95, it doesn't work right. Like that seems almost half, right? Yeah. What is 96 is 48 is half of 96, right? Oh, all right. There we go. Any questions from home? We're just gonna let Olivia take the whole thing, huh? Yeah. If she questions it, I probably should too. Yeah.
I have a question, but it's on the review. It's just like on page. I don't wait. My packet's messed up. So it's the page that says use ice charts where possible. It's the first one.
Use ice charts if possible. Yeah. Okay. I'm there.
Okay, on the first one, why don't we double the? I mean, why do we like? Yeah, why don't we double the 0.5?
I got page 17 for that. Why don't we double the 0.5?
Because don't you normally do 2 times the number, or is it because it's like I don't know, I don't get it.
It's the concentration.
Oh, so you don't. Okay.
Yeah. When you double this, the concentration of NO2 is 0.5. I think what you might be thinking about is the doubling that we do here sometimes, or tripling that we do here. This is different because the concentration of Al is 1 for every 3 of these. That's why we triple it here. Don't do that here because they actually are giving us, they say the concentration is 0.5.
That makes sense.
Blah, blah, blah. Yes. This past Monday, what did we do? Oh, that's KSP. Solubility product constant, yeah, there'll probably be like 1 or 2 questions, yep. It probably wasn't. It is part of all of it. Like, I mean, it's the same stuff as ice tables and all that. It's just considered easier. It's like that one thing, like you do it, you spend a little time on it, and it's easy. But if you don't go back and review it, I guess probably should put it on the review. But if you don't go back and review it, then kind of weird, right? Page 13 and 14. Eight A. At equilibrium, the system contains, yeah. Um, So if we take a look, let's take blah, 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 blah. I'll set it up. K equals COCL2 and CO and CL2. So if there was a 2 up here, you would multiply K by both of these and then square root that, both sides, and that would give you the concentration. Yes. No, because currently that is just X. It's not 2X. That is just X. Because that's the concentration. The 2 goes out here. It doesn't go in here. I think that's similar to Margot. You guys are having trouble with that. The only time you do that stuff yes. That's big. That's that. Okay, I see what you're saying. Like right here, we have 2x squared and then x. So yeah, this 2x is that concentration. And then the other problem, it is just x. It's not 2x. It is the concentration. Okay, let's go. Yep. So if we take a look, be able to explain the changes. So that's a huge one. Like that's all the shift, right? A change in pressure can affect the gas system. Concentration can affect anything. We add or remove things, that affects it. Temperature, heating or cooling, any of those changes would affect it. Yep. And that's like this page right here with the up and down arrows. Does adding a catalyst do anything? No, right? So adding or removing, increasing or decreasing temperature, or changing pressure. Those are all the things that affect it. And be able to determine how the amount of products can be maximized. So if we have a system at equilibrium, we have reactant yield products. Basically, we want you to know how to maximize that. So by adding more reactant, we would maximize products. By removing products, we would make more products and maximize it. We'd have to look at the pressures, like the number of moles, to determine how affecting the pressure could maximize products. We'd have to know that if it was endothermic or exothermic, how we could maximize products. We'd have to know the temperature, like the endo or exo for it. Any others?
On like the ice problems, how do you know which side to like subtract x from and which side to add?
So it all depends on which way the reaction is going. Remember, one of our statements said that at equilibrium, you have to have a part of everything. You have to have something of each thing. Anytime you have a 0, it's going toward that direction. But it's got to have at least some of that. So anytime you have 0, that reaction is favored in that direction. So we know that we're subtracting from the other side and adding to the other side. This problem here, we had some of everything, right? So we had to find the quotient, which is Q. And Q was 0.375. We then looked how Q compared to K. Is 0.375 greater than or less than 0.01? It's greater than. So we have to go in the reverse reaction way. If Q is greater than K, then reverse reaction is favored. So that's how we knew on this one we were subtracting from here and adding to here.
Okay, so if there's no zeros, you use like Q and you compare it to K.
You got it. Yep.
Okay, thank you.
Be able to explain Le Chatelier's principle. Basically, Le Chatelier's principle says that the system, if stressed, a stressed system will return to equilibrium. So if you remove something, the system is stressed, it will make that something. If you add too much of something, the system is stressed, it will use that stuff up to turn the into the other stuff until it gets back to the ratio needed. If we heat the system, it will alleviate making products or reactants depending on if it's endothermic or exothermic. System will return to equilibrium. You like it? To tell you the truth, if it weren't for ice problems, this would be pretty easy, right? But the ice problems, you can get turned around very quickly, and then it's like. It looks like it. No, we won't do that this year. What I could do is I could make that last test the final day. I don't know. Not close enough yet to determine. Right? Yeah, we did not get to 1 unit this year, which is actually kind of impressive. Oxidation reduction. Basically, it's probably one of the most important units if you're going into engineering, because it's basically how they make batteries. If you wanted to go work for Tesla, it would be the most important unit for you. Right? Sorry. I can put together a package you can work on over the summer if you want. You sure? It doesn't look like we're going to get through. The only way I could imagine it is if I taught you just oxidation numbers like the week of the finals, that's what I got, guys. Unless you guys have more questions, you can get off here, Hudson, with quit taxing your internet. How many people do you have working from home right now? Should we give him like latent time to answer? He's got to be playing like Call of Duty. Right?
Wait, are you talking to me again?
Yeah, is your name Hudson?
I literally heard at home. I heard at home and then something else. It was like completely cut off.
Working from home right now. Is it you and like a couple brothers and sisters and parents, or what?
My sister is in person, and then my parents are at home.
So there's 3 people on the internet. What's your mom playing?
I don't think so.
Oh.
It's really weird because when I'm like actually on games, I have like super low ping and stuff. The Wi-Fi is great, and then as soon